that we can use. Okay.
I'm sorry for interrupting a little bit. Like I think it's better to record Dr. Ma's workshop. And so I just starting the functioning, initiate the recording, and I think we will be able to post the recorded like video through the NCME website through our SIGME. Yeah, thank you.
Thank you. So the goal of CDM, basically cognitive diagnosis, is to identify what students have mastered and what they have not yet. So, but there are multiple ways that we can achieve this goal. But a CDM or cognitive diagnosis models are one possible approach that we can adopt. So CDMs are latent variable models for cognitive diagnosis. So you can see the goal is to identify what students have mastered, what they have not yet. But there are also latent variable models, which is another key term. So they are used to establish the relationship between latent variables and observed variables. So typically observed variables are items in assessment, say for example, and the latent variables here, or the observed variables, are called attributes. So those are what we want to make inference about, okay, based on CDM analysis. And CDMs are more dimensional in nature because most of, well, I say in general, this is the case, but sometimes we can also handle a situation where there's only a single latent variable, and we can still use CDM, but most of the time, CDMs are more dimensional, which means we want to handle multiple latent variables or multiple attributes at the same time. And CDMs are a big family of models. There's so many different CDMs, and they are parameterized based on different assumptions or different theories about how students solve test items. Okay, so if you have different assumptions, you may need to use different models. And sometimes if you find that, well, all those existing models may not fit my theory or my assumption, then in that case, you may need to develop a new model to better capture the nuances in problem-solving process. Well, there are many different names for CDMs. That's why if you read some literature in this field, you will say, well, there's just so many people use different terms to refer to the same thing. So one popular name is Diagnostic Classification Model, so DCM, but there are also other names. So I just want to make this clear so that we will be easier when you read the literature. Okay, so attribute is a key term in CDM literature. They represent the latent variables. So they could be any procedures, skills, or processes that involve in the problem-solving process in cognitive tests. Okay, so many times we want to make inference about students' attributes. We want to know, what they don't know. But more generally, beyond the cognitive test, they can also represent some psychological characteristics that may affect individuals' responses to test items. So those may include like psychological disorders, psychological personality, attitudes, and so on. So which means CDM can be used not only in cognitive tests, but also in other situations like psychological test situation. And most of the time, attributes are assumed to be discrete latent variables in CDM context, and most often they are assumed to be binary latent variables, which means each attribute will have two statuses. Typically, we use 0 and 1, of course, because they're binary, we can use any two numbers. But most of the time, we use 0 and 1. And in cognitive tests, we typically consider two status as non-mastery and mastery. So most of the time, 0 indicate a non-mastery and 1 indicate a mastery. So that's why we want to say, well, after the CDM analysis, we will know the attribute profile for each student. And that profile indicates which attributes have been mastered and which has not been mastered. Okay, so you can see that that attribute profile contains the information about the mastery status using binary vector 0 or 1. Okay, so here is a toy example. It's very simple. So suppose a math test is created to measure 3. So k is equal to 3. So I use k to indicate number of attributes. 3 attributes: addition, subtraction, and multiplication. So you can say this is a very a simple example. So each of those 3 attributes is assumed to be binary, as I just mentioned. 0 to indicate mastery status, and 1 to indicate mastery, and 0 to indicate non-mastery. Okay, so for each attribute, we have these 2 statuses. So you can say, well, mastery for addition, non-mastery for addition, mastery for subtraction, non-mastery for subtraction, and so on. Okay, and here are 3 example items that measure or involve those 3 attributes. And a key point here is that some items may measure more than 1 attribute. Like the first item, 3 times 4 minus 2 measures both multiplication and subtraction. Okay, so this is particularly important if you have some item that may involve a lot of different cognitive skills. So sometimes it's difficult to measure each attribute individually, but in this example, it won't be too difficult. You can have 10 addition questions, you can have 10 subtraction items, and so on. So you can measure 3 attributes sort of separately using different items, but sometimes it's not possible to separate some attributes. So that's why in CDM, we allow those items that measure more than 1 attribute, and many times this is more realistic. And the primary goal of CDM analysis is to estimate individuals' attribute profile. So the profile can be denoted as a vector, basically. So if we have 3 attributes, it will be a vector with 3 elements, like here, addition, subtraction, multiplication. So basically, we need to have 2 pieces of information as the input for CDM analysis. One is the data side, which should be a student by item matrix. This is the item response matrix. And the other input is basically the Q matrix. This is an association matrix between items and attributes. So it tells us which attributes are measured by each item. So you can see the first item here, 3 times 4 minus 2 measures subtraction and multiplication. So we use 1 to indicate that this attribute is measured by this item, and 0 indicates this attribute is not measured by this item. So you can see that's why the first row in the Q matrix here has 0, 1, 1. It means the first item measures the second 2 attributes. Okay. And the second item, 6 minus 1, measure the second attribute, the subtraction, but not the other 2. So with these 2 pieces of information, data and Q matrix, we can start the CDM analysis. And we will talk about that more very soon. But the output of the CDM analysis is the attribute profile for each student. Like for the first student, maybe based on his or her responses, 0, 0, 0, we can make inference about his or her profile like 0, 0, 0, which means the student doesn't master any of those 3 attributes. Okay, and the second student has a profile 1, 1, 0. That means this student mastered the first 2 attributes, but not the last one, and so on. So you can see, based on the data from each student and based on the Q matrix, we can use some CDM, and eventually we can get the estimated attribute profile for each student. And that will tell us which attributes have been mastered by each student. Okay, so this is the primary goal of CDM analysis. But as you can see, sometimes we say, well, we are estimating students' attribute profile, but we can also say that we are classifying students into different latent classes. So because many times we say, well, each profile indicate a unique latent class. So student 1 is estimated to have a profile 0, 0, 0. We can also say, well, student 1 is classified into a latent class with a particular attribute profile 0, 0, 0. Okay, so there are 8 possible attribute profiles for this example. So we say, well, there are 8 latent classes. So you can see whenever we give a student attribute profile, we actually classify that student into the corresponding latent class. Okay, so you can see these 2, they're equivalent. I mean, estimating students' profile, or you can say, well, we are classifying students into different data classes, okay? Well, although the primary goal of CDM analysis is to either classifying students into different classes or estimating their attribute profiles, but to make sure the classification or estimation is reliable and valid, we need to check many other things. Okay, so the first one is we need to make sure that items have good psychometric properties. So many times we can examine the item parameter estimates. We can say, well, whether those items have good discrimination index, whether they have performed well. And we can also check the differential item functioning, because that's quite important in psychometrics to make sure the scores or classifications are comparable for different groups. And also, we need to make sure that the items measure what they are designed to measure. Say, for example, here we have the Q matrix, which is a very important input for CDM analysis. And we say, well, the first item measure the second two attributes, and the second item measure the second attribute, and so on. So you specify a particular item attribute association. So which means assume that association is correctly specified, but that can be wrong or to some extent. So that's something we need to validate typically, okay? And also we want to make sure the CDM that we use can fit data adequately. So as I mentioned a bit, well, there are so many different CDMs in the literature, and you can use different models here, but we want to make sure that the model that you use can fit data adequately. Okay, that's about model data fit. And also, when we classify students into different learning classes, we want to evaluate whether the classifications are reliable or not. So we can calculate the classification reliability empirically. So that will allow us to get some sense about the classification reliability. Okay. So in what follows, I'm going to first discuss a few CDMs quickly, and then we will jump into the R session and see how to use the R package for CDM analysis. Well, in this webinar, we are going to focus on the CDMs for binary data and binary attributes. So as I mentioned at the beginning, what attributes? Also, I have a question.
Yeah, Dr. Ma, sorry. A quick question.
Yeah.
Okay, thank you. So my name is Justice Dazi, PhD student in the University of Alabama, Educational Research. Yeah, so I'm a first year student. Now, my question is this. I'm trying to do a study on which I want to use the CDM as a model, but the study looks at trying to find out a standardized test, which is 50 items, but I'm trying to use the table of specification as my attributes, where I'll be able to identify each question and each attribute, whether if it is measuring knowledge, if it is measuring understanding, if it is measuring analysis, application, this Bloom's taxonomy attributes to the items. So I want to administer that standardized test, so that I'm going to just score it as in 0, 1, 0 being not mastered, 1 being mastered per items. So based on the attributes, I'm going to have more than one attribute than the binary attribute. Is it going to be efficient to use the Rash model, or the CDM will still perfectly match the study?
So did you say you're going to have more than one attribute?
Yeah, because I'm going to have 50 items and the attributes are in 6 different attributes. So I have knowledge, understanding, comprehension, analysis, application, and these are the attributes. A particular item may have or measure 3 or 4 attributes within the Bloom taxonomy. So let's say question 1 could measure application at the same time, it could measure knowledge at the same time, it could measure, let's say, understanding, but it may not measure analysis, comparison. So that would be 0, 0, 0. So I may have that question 1, I may have 1, 1, 1, 0, 0, 0.
Okay, so your question is whether you should use a CDM model
Or
or
the model.
well, you won't be able to use a unidimensional Rush model. So do you mean the one-dimensional Rush model?
No, I'm just asking because I'm getting confused here, whether to use the CDM or the Rush.
Oh, first of all, based on what you described, I think you have multiple latent variables, which means you will choose either a CDM model with 6 attributes or a more-dimensional Rush model with 6 dimensions, right? So
Okay.
I think the decision will depend on what you want to achieve. So a Rush model is a latent treat model, which means it will put the students on 6 different continuum, but CDM will give you 0, 1 classification for each attribute. So you need to decide as a researcher which type of results desired in your situation. So I think that's the primary consideration. And the second consideration is about the model specification. So Rush model based on a particular a formula, and CDM have, there's just so many different CDM models. So those different model specifications will also affect how you build a relationship between item responses and attributes of dimensions, right? So you need to decide, well, which one will make more sense theoretically or conceptually. And also you can do the model fit evaluation. That's sort of empirical evaluation to see which model can fit it better. But I think those are some considerations that you need to you need to consider. Yeah.
Okay. Thank you so much.
Yeah. Thank you. So let's continue. So we will focus on the binary data, binary attributes, but keep in mind that CDMs can handle polytomous data and polytomous attributes. Okay. So there are a large number of CDMs in the literature, so I need to move really fast here. So let's assume we have k binary attributes, then we have 2 to the k attribute profiles. Say, for example, if you have 3 attributes, then we're going to have 8 different latent classes, and here are their corresponding attribute profiles, like 0, 0, 0, 1, 0, 0, and so on, okay? So all CDMs that we're going to discuss below have a general form. Say, for example, for atom 1, it can be written in this way. It's sort of a silly formula. So the probability of answering the first item correctly given alpha, which is the attribute profile, is basically a function of all your 3 attributes. Why do you know them? That will affect the success probability. Okay, so it's simple. But keep in mind that this item only measures 2 attributes, which means it doesn't measure addition. In that case, whether you know addition or not should have no impact on your performance on this item, right? So in that case, we can actually reduce the 8 latent classes into something we call latent group. So here we use 4 latent groups because whether you know addition or not, it doesn't matter for this particular item. But because CDMs are item level models, so we need to build a model for each item separately. So for item 1, we will only consider which attributes have been measured by item 1, only subtraction and multiplication. So we can combine the first latent group, the first 2 latent classes, 0, 0, 0, 1, 0, 0, because students in these 2 classes do not master subtraction and multiplication. So they should have the same success probability for item 1. That's why we can combine them, and we will call them latent group 1. And we use a reduced vector. We call this alpha LG star for 0, 0. Okay, so you can see alpha LG star is the profile that will really have an impact on student performance to this particular item. Okay, so that's the distinction between latent group and latent class here. And this matter because we use the same notation in the package, okay? So based on the alpha LG star or latent group notation, we can write the formula, we can modify the formula a little bit for item 1. Now it becomes the probability of answering the first item correctly, given your reduced attribute profile, is a function of whether you know subtraction and whether you know multiplication, okay? And now let's move to 2 specific models. They are very popular, and one is called DINA model. It was developed a long time ago. The item response function can be written in this way. But let's move to the bar chart is easier to understand. So for the model, it basically assumes that if you do not master all required attributes, you all have the same success probability, and we call it guessing. Okay, so as you can see from this bar chart, this is for item 1. If a student have a profile 0, 0, 0, 1, or 1, 0, they all have the same success probability. Okay, that's called guessing parameter. Well, if they know both attributes because both are measured by this item, then they have typically a higher bar that represents their success probability. Okay, so here we use delta G0 to indicate the success probability for those 3 bars, and delta G0 plus delta G1 indicate the higher bar for the last group. Okay, so you can see delta G1 is an increase by mastering both attributes. Okay, so we use delta parameters here for item parameters. Okay, but you can see that sometimes we are not only interested in delta parameters, we're also interested in those bars because they are very easy to interpret. Okay, that's why later I will show you how to get those success probabilities from the package directly. Okay, the other popular model is called generalized Dina model or GDINA model. It is a little bit more complicated from the formula side, but from the bar graph side, it's actually very similar to the Dina model. And the only difference is now different latent groups can have different success probabilities. Okay, as you can see for item 1, there are 4 different latent groups, and we need to assign 4 different parameters to represent their success probabilities. Okay, so that's why if you have the number of parameters for GDINA model is the same as number of bars in your bar chart. Okay. So now what we want to do is we want to figure out how to estimate attribute profiles for students and how to get some useful information for items. Okay. Well, I assume that you have already installed RStudio and also the GDINA R package. You can install GDINA R package easily from RStudio. And I also sent a link in chat box, a chat window, where you can find the data set and Q matrix. Okay, so you can download data 1 and Q1, and we will use this one for illustration purpose. Well, first of all, we read the data into R, so you can have a look at the data format. So the data set has 837 individuals, and we have 15 items, and this is binary items. You can say 0 means incorrect response and 1 indicate a correct response. And there are 3 attributes. And the Q matrix looks like this one. With read table to get the Q matrix is 1, 0, 0, 0, 0, 1, and so on. So you can see the first item measure only the first attribute, but the last item, item 15, measure all 3 attributes. Okay. Well, how do we use the GDINA function for CDM analysis? Well, first of all, the GDINA function, the GDINA is the main function that we want to use. It can be used to estimate different CDMs, but we just need to specify which model we want to use. Well, to do this, let me go back to my RStudio. So we can do this together. So let me load the this one here. Using this one. That would be easier, but it will allow me to run here. Okay. So first of all, we need to use library. Well, you can copy the code easily, I think, from the handout. So you can just copy the code and paste. Well, first of all, you need to read the data and Q matrix. And then you can run the library GDINA, which will load the GDINA package. And then we say, well, we have fit 1 GDINA, and then we need to specify basically at least 2 things, the data and the Q matrix. Okay, the first input is a data matrix. The second one is a Q matrix. And the third one is actually your model, but by default, it's the GDINA model, which means even if you don't specify it, it will still fit the GDINA model for you. Okay, so if you run this one, first. run this one. Okay, I will give you some outputs. At basic print the number of iterations and some maximum absolute change during the estimation process. So the fit. We put the regional estimate into something called theta 1 here, as you can see. It contains almost everything that we need. We call it an object of class GDNA, and we can use different methods to get information from it, okay? So first of all, we can print some summary information from theta 1. And the easiest thing you can do is just type theta 1 in your RStudio, and then you will be able to see those things. Let me type theta 1. This. Move this one. So if you type theta 1 in your RStudio, it will print some information like which version are we using right now, and then some data information, number of individuals, number of groups, and number of items. And also it tells you some information about the model that you are using. And you are estimating a general model, and you have dichotomous attributes. And the attribute structure is about whether you have any particular model to model the attribute association. Okay, the saturated here basically mean, well, you estimate a saturated model, which means you do not have a specific structure for your attributes. Okay, it's a default setting. And you have 288 iterations, and it converge, as you can see here. Whether it converge, yes, it converged. And there's some other information. This time used is 0.4799 seconds. And another function that you can use to get useful information from theta 1 is summary. If you copy summary theta 1 and paste into your RStudio, like here, then you will get more information. And the first part is about test fit statistics. Okay, you have our ASCBS, CCS, and ICBS. Those are all information criterion. And then there's some number of parameters. The total number of parameters is 67. And it split this into different type of parameters, like number of estimated item parameters, that's 60, and number of fixed item parameters, that's 0. So which means we actually you can fix some item parameters, but estimate other item parameters, that's okay. But in our example, we didn't do that. And the number of distribution parameters is 7. Well, here, recall that we have 3 attributes, which means we have 2 to the 3, 8 latent classes. And we have 7 distribution attributes because we are estimating the proportion of students in each latent classes. Okay, so you estimate the proportion of students in 000 group, the proportion of students in 100 group, and so on. But you know that the total of those proportions must be equal to 1. That's why there are 8 proportions, but we only need estimate 7 of them. And the last one can be calculated. So that's why we have 7 parameters here. And the last part is called attribute prevalence. Okay, so this is about the proportion of students who master each attribute. And we label that as level 1. And level 0 means the proportion of students who do not master that attribute. Okay, so say for example, for attribute 1, based on the general model, 36.88% of students are estimated to not master this attribute, and 63% of students are estimated to master this attribute. Well, we use level 0, level 1 because if attributes are polytomous, we will have level 0, level 1, level 2, level 3, and so on. Okay, so otherwise, I mean, you should just interpret them as non-mastery and mastery. Okay, it'll be actually easier for binary attributes. That's about summary function. Okay, so those are 2 useful ways that you can print some summary information. So now let's move to some item parameters. So recall that I showed you the bar graph. So that in the bar graph, you have those success probabilities. They tell us about the performance of those items. And here, we can also get the item parameter from the general estimates. the function that we are going to use is called coefficient, COEF. This is a built-in function in R actually. So if you do linear regression before, you must use this before. Okay, so it's coefficient, and the first input is your G-dinner estimate, theta 1 in our case. Okay, and the second input is what? What means what are you going to get from this function? It can be cat prob. Cat prob means the category probability. That's basically the bars in the bar chart. Okay, and let's try this first. Oh, delta. So we can try delta first, because recall that in the model specification, the DINA model and the GIDA model, we say, well, the probability of success is a function of deltas. So delta are the model parameters. So you can specify delta there as what argument, and then if you run this one, the coefficient object is theta 1, because that is general estimates. What is equal to delta while requesting delta parameters. Okay. So this is delta parameters from the estimation. As you can see for item 1, recall that the Q matrix, in the Q matrix, item 1 only measures a single attribute. That's why you only have delta 0 and delta 1. Okay. And delta 0 is basically the guessing parameter, and delta 1 is the improvement in your success probability if you master that required attribute. Okay. But for item 5, as you can see, since it measures 2 attributes, that's why we have delta 0, delta 1, delta 2, and delta 1, 2. That's the interaction due to the fact that you master both attributes. Okay. So this is delta parameter. And we can also request the item success probabilities. Okay. This is the conditional success probabilities for different latent groups. Keep that in mind. Okay. So here, in addition to specifying what is equal to cat prob, which means item probability, we also specify with SE being true. That means we also want to estimate the standard errors for item parameters. Okay. So now you can see, let's go back to item 1. So for item 1, now we have P0 and P1. So P0 means the probability of success for those students who do not master this attribute. Okay, so P1 means the probability of success for those students who master this attribute. And we have their corresponding standard errors. Well, if you have 4 latent groups, then you will have 4 different success probabilities, because this is GIDA model. If you fit a DINA model, then the first 3 values here will be identical. Okay, because that's the assumption of the DINA model, right? But for GIDA model, you will estimate those probability of success separately. Okay, so which means for each latent group, they will have different estimates. So this is about the item success probabilities. And you can see, well, sometimes we need to take closer look at the item parameter estimates. If you check the item 1, you will say, well, if I do not know that attribute that is measured by this item, I can still have a very high success probability, like 0.9291. That's really high, right? You may ask why, right? That's something we need to figure out if we are doing analysis. We may need to discuss with the domain experts. Say, well, does it mean this item may measure something else? Or maybe this item doesn't measure what we think it measures here in the Q matrix, right? Because otherwise, why then you master this attribute has almost no impact on success probability, right? Although, well, there's still some tiny differences between these 2 probabilities, but it's trivial basically. But that's something that we can discuss with domain expert to reevaluate this item, I think. And another, if you take closer look at some of those items, let me show you. Like this one, item 10. You will see that, oh, P00, which means the probability of success for those students who do not master any of these 2 attributes, okay, is 0.43. But if you master the second attribute, your success probability is about 0.36, which is even lower. That's strange, right? Why does your success probability even lower if you master a required attribute? Okay, and also, as you can see here, P10 is almost the same as P11. So I would feel that, well, it seems that P00 and P01 are so close to each other, and P10 and P11 are also quite close. So maybe the second attribute doesn't matter for this item. Okay, so they won't be identical because, I mean, you are estimating them separately. So, but they are just so close. So there's something we can consider when we check node item parameter estimates. Okay, so let's move to the next part. Recall that I just mentioned node item success probability are for different latent groups. But recall that for this test, there are 3 attributes, so we have 8 different latent classes. You can get those success probability for different latent classes. You just need to change the what argument, okay? So you can use what is equal to LC prop, means latent class probability. Then you will get a matrix. In this matrix, you have success probability for different items and for different latent classes. Okay, like 000, 100, up to 111. Okay, but there's no way for you to request an error in this case. But you can get an error from the previous output. Okay. The other thing that sometimes we're interested in is the Gaussian and sleep parameter. So these 2 parameters are particularly relevant for DINA model. So Gaussian parameter is the probability of success for those who do not master all required attributes, and sleep parameter is here, is the probability of failure for those who master all required attributes. Okay, so for any model that you fit in the general package, you can always request Gaussian and sleep parameter. But they are just the first column here and 1 minus the last column in this matrix. Okay, so they are identical as the traditional definition in DINA model, but in some more complex model like traditional model or other model, there are no particular Gaussian and sleep parameters, but we can still get those 2 type of probabilities for you to check the item performance, and we still call them Gaussian and sleep, but they are not really the parameters that are used to define the model. Okay, so we need to be careful when we request the GS. GS means Gaussian and sleep. Okay. Okay, so those are about item parameters. So let's move to person parameters. For person parameters, we need to use a function called person parm, means person parameter. Okay, person parm. And the first input is still the GDNA estimates, theta 1. And then you need to specify what. So what could be EAP, MAP, MLE. Those are 3 sort of conventional estimation procedure for estimating attribute mastery status. Okay, and they're also used in ART context. And the last one called MP, it represents the mastery probability. So if you request MP, you will get the mastery probability for each student, for each attribute. Okay, so let me show you this one. I use a head function because otherwise it will be very lengthy. So if I use person parm theta 1 and I do not specify what argument, then by default I use EAP method. Okay, so you can see the first student is estimated to have a profile 111, and the second student have a profile 001, and so on. Okay, so what if I specify what is equal to MAP? So I'm using MAP method. So now you have in the first 3 columns, the estimated attribute mastery status for each student, but you have another column called multi-modes. This is used to indicate whether you have multiple modes in your posterior for that particular student. Okay, so false means no, there is no multi-mode, so this is a unique solution. But if you get a true here, that means this solution is not a unique solution. It is one solution that we randomly selected from those modes. Okay, so that's one thing we need to be careful. And the same for the same can be said for MLE. So we also have a column for multiple modes. That is used to indicate whether you have multiple modes in your likelihood. Okay. What about MP? If you specify MP here, it gives you the mastery probability for each student on each attribute. You can see the estimated mastery probability for the first student is 0.41 for attribute 1. Okay, and actually EAP is converted from this matrix. So we compare this matrix with 0.5, and then we got the EAP estimate. Okay, so after you have this matrix, the mastery probability, you can actually change the cutoff. You say, well, I don't want to use 0.5 to indicate mastery or non-mastery. I want to use like 0.3 and 0.7. So you can make that decision. So you can get a new estimate from this output. Okay. And there's some function we can use to draw plot to get other information from the regional estimates. So you can use plot function, and the first input is always regional estimate, and what can be IRF means item response function. Okay, and you can specify which item you want to draw the plot for, and you want to include some error. And then you will get those bar charts that I just showed you previously. Okay, this is for item 9, and this is for item 15. Okay. And for person master probability, you can use plot function again, but this time you need to specify what is equal to MP, means master probability. Okay, and you also need to specify which person you want to draw the plot for, at person 1 and person 5. And you can see this plot can be used for person comparison, but you don't want to compare too many persons at the same time. Will be too crazy, too busy in that case. Well, you can also use extract function to get a lot of outputs from information from the regional estimates. And one useful information is the posterior probability for each latent class. So you can use extract. This is your first input regional estimate, and what is equal to posterior prob. Okay, this will give you the posterior probability for your estimate. Okay, and if you use the extract, if you search the help page, you can get the list of things that you can extract from the regional estimates. I think that would be very helpful if you want to try. Okay, there are some other considerations in model estimation. So I just give you an example about how to do this. But there are other things you need to consider typically when you feed a CDM to a set of data. Like, do you want to consider monotonic constraint? Like, do you think the probability of success for 0-0 group is higher than the probability of success for 1-0 group is reasonable? If you don't think that is okay, you can impose a monotonic constraint so that the probability of success will be higher when students master an additional attribute. Okay. And also sometimes we say, well, attributes may have some particular relationship, like they may have hierarchical structure, like attribute 1 may be required before you master attribute 2 and so on. This is something we can specify when you build a model. And also sometimes you may say, well, I think there are an overall ability which affect the mastery of those attributes. So that will allow you to build a higher order model for you. Well, we can, and the package can accommodate all those specifications, but I mean, those are sort of theoretical consideration before we do the analysis. Well, we published a paper in 2021 to build a sort of analysis flowchart. So, well, we may want to follow the procedures for CDM analysis. So I work this with my students and also collaborators. So I think this is a very interesting paper. So we discussed, well, we may want to do Q matrix validation first, and then finalize the Q matrix, and then do model calibration and model fit evaluation, and then we can do some item diagnostic information evaluation. And the last step could be the classification reliability evaluation. Okay, but the key point is we want to interpret the result, and we want to also collect some validity evidence if possible. Okay, that can be sometimes a challenge. Well, I will go over some of the analysis quickly. So for Q matrix validation, this is a very popular area in the field, and there are many different Q-matrix validation procedures in the literature. And the package has several implementations. So this is one of them, and it's not that difficult actually. After you have the regional estimates, that could be your first input for the Q-vol function. And then in the second input method, you can specify different methods for Q-matrix validation. And if you go to the help page, you can get more information about which method you can consider, okay? So in our case, let me show you quickly here. Well, keep in mind that, this is the output. As you can see, the star here denote a modified element. So this is Q matrix, but only a few have those stars. Because atom 10 is 0, 1, 0, means original Q vector for atom 10 should be 0, 1, 1. And now the suggested Q vector is 0, 1, 0. Okay, but keep in mind that this is just statistical recommendation, and you do want to bring this back to domain experts to say, well, let's check those items. This procedure suggests a modification to this item. And do you believe this is the case? So I think this needs to be used with some caution. And I think this is true for all data-based Q-matrix validation procedure, okay? And also for model evaluation, there are two functions in the package. One is called model fit, and the other one is called item fit, but it doesn't sound like, okay, so model fit is for model fit, and item fit is for item. That's not necessarily the case. So item fit also provides some information for at a model level. Okay, so, but let me show you quickly. If you use a model fit here, it will give you some relative fit information based on the information criterion. It also gives you some absolute fit statistics. This is based on the limited information statistics M2. And it report the p-value here. And this is a hypothesis test. So basically, no hypothesis is that the model can fit data well. An alternative is the model cannot fit data well. So you can say you can interpret the p-value just as the traditional hypothesis test, okay? And we also report the RMSEA2, which is sort of an effect size measure. And SRMSR is also an effect size measure, okay? So you can see you can combine those things. Say, well, you have hypothesis size results, you also have effect size measures, okay? And for item fit, I think it can be particularly useful when you find that the model may not fit data quite well. So the item fit will allow you to check, let me see, oh, this fits just so good. So it will give you a plot that will show you whether those atom pairs fit well. So basically we have a model-based atom pair association, which could be the transformed correlation or the log odds ratio. And we have the data-based transformed correlation and log odds ratio, and we compare them to see, well, whether they are close enough to each other. And we also have a hypothesis testing here, but for this data set, they all look good, okay? But if you have a real set data, you may have some red place here and there that will allow you to say, oh, maybe this item and that item have some strong connection that the model cannot account for. So in that case, I think it provides some really useful information to identify where the misfit come from, okay? Okay, we only have 9 minutes left. So I think we can do the exercise at home. So we can have some time for questions. Any questions? And I just want to remind you that here we also have some additional information. It gives you a long list of about what this package can really do for you, although we only cover a small portion of those possible analyses in today's presentation. And also there are more learning resources that can help you to use this package to do CDM analysis, okay? So any questions?
So I just want to jump in. Thanks, Dr. Ma, very much. I know it's like just 1 hour, so we can only cover the very important and then most practically useful part of the analyzing CDM using R. But I think this will be very helpful, especially for your handout. And I'm recording the section, so I think they can following the like a recorded video. And we do have a question in the chat. So they ask, how does the package handle missing data?
Thank you. That's a very good question. Let me see. I cannot see. Okay, here. So the package will handle the missing data using the full information approach. So basically, the missing value will not be taken into account when we do the estimation. So say, for example, if a student answered 40 out of 50 questions, and there are 10 missing data points for that student. So when we do the estimation, we will only use those valid data, and we will ignore the missing data. So that it will be handled by the full information likelihood directly.
All right. So I see Justice. You have a question you can ask.
Yeah, thank you. Okay, so my question is this. You used an example of the 15 items. So if I have 50 items, then I have 50 items, then I have 7 attributes to each of the items. Then as you must your example, the example you used, the last item really measured the 3 attributes. So that you might have 7 attributes, 50 items, but I'm only using the binary, kind of collection that is 0 and 1. So my question is this: if you administer the instruments, let's assume an exams, and they write the exams, and it's like one multiple choice with let's say 4 options, but you're going to code it as in 1 correct, 0 wrong, 1 correct, 0 wrong. Is it going to be able to take care of those students that do not answer any question? Because I don't intend, though you did not answer the question, it should be 0, but I don't intend giving 0. I intend leaving it blank. Is the CDM going to take care of that missing values if I don't include them as in zeros?
I didn't hear you very clearly. So your question is about what if you have one item that measures, say, for example, 7 attributes?
Yeah, my question is, I'm going to administer 50 multiple choice questions in A to D, and I'm going to code them as in 1 right, 0 wrong. And each of the items, I have 7 attributes that is being measured by each of the items. So one item could measure 3 attributes out of the 7. Some could measure 4 out of the 7 attributes. So I'm going to use 0 and 1 for 1 being mastered in terms of the attributes, 0 mean not mastered in terms of the attributes. Then 1 means correct for the responses, 0 means wrong. And my question is, I do not want to give a score either 0 to a student that did not attempt the question. So ideally in an examination, if you don't attempt the question, it should be 0, as in you got it wrong. But I don't want to give them a score. I want to leave it blank. Is the CDM going to take care of that missing values if I leave it blank?
Oh, yes. So the question is, in multiple choice questions, what if we have some missing by design? Say, for example, some students only answer the first 20 items, and some students, say, for example, only answer another part of questions, and there are some missing value that cannot be treated as 0 or incorrect response, right? So they will be treated as a missing value. That is totally fine. So the package can handle missing data directly. So basically, when you estimate that student attribute profile, we will only use the information from that student's valid responses. So the missing data will not be considered in that case.
Okay, so second question, will the model be able to determine the difficult index and discriminatory index of each of the items for me?
Yeah, well, that's a very good question. So whether the can the model calculate item difficulty and item discrimination index, right?
Yeah.
Yes, but there are just so many different ways to define item discrimination in CDM because CDM is a more dimensional model. So even in ART, when you have more dimensional model, the discrimination can be a little bit tricky, not that easy to interpret. So you need to in general package, we have two ways to calculate the item discrimination. One is basically P1 minus P0 recorded in the item parameter outputs. You have P0 and P1, right? It's probability of success for those students who do not master all required attributes and for those who master all required attributes, right?
Yeah.
So this is one way to calculate discrimination. We just use P1 minus P0. And only consider these two extreme group. So that's discrimination. But I am not aware of how to calculate item difficulty actually for CDM models. So that's why there's no way to calculate the item difficulty index. But I think that's a very good point. And you can explore to say, well, how can we define item difficulty in CDM context?
Yeah, that is what I'm trying to figure out. But it looks like even with the discriminatory index, the group has to be divided into 3 subgroups, as in the upper group, the lower group, and the middle group. But I'm not going to consider the middle group. So I'm going to do the upper group minus the lower group to get the discrimination, whether either item discriminated well or not. Now, that is one thing.
I'm sorry. Sorry to interrupt because we just have 1 minute left. And then I think Justice, you asked very excellent questions. And I encourage you to follow up with Dr. Ma, maybe for further detailed discussion. I want to give another like a 1 or 2 audience to ask a general question. So I see the Enya Ma is in the so you can ask question if you have.
Yeah. Hi. Thank you. Thank you, Dr. Ma, for the excellent workshop. I just have two very quick practical questions. One is there any sample size, because it is a complex model, so is there any like a sample size requirement to make this, like to run this model valid? I know like for ART, maybe like 200, 300 responses will be fine, but how about the CDM? And my second question is like CDM has like it's a big family. So like, do you have any suggestion about order of the model that we should start to try from the beginning? Yeah.
Okay, thank you very much. Those are very good questions. The first one is about sample size. Well, I don't think there is a rule of thumb at this moment. Although in one of my simulation studies, we found that even for like 30 or 50 students, I can still get quite good estimates using a very complex model, regional model. But I think the idea is there's so many different factors that will affect your performance, the model's performance, like whether your items have good quality, and whether the students have a lot of guessing behavior and so on. So those will all affect the model's performance and the classification accuracy. So I think it will be difficult to give a specific number. But I feel that but it's always a good way to say, well, you can always do a small simulation study to try, well, if I have this type of item quality and I want to use this type of model, then what should be the sample size in order to have a particular like classification accuracy. So I think that's something you can consider as a sample size planning. Okay, and the second one is about the order, because we have so many different CDMs. So which one we should use? So I would actually recommend, if you have, there are several different considerations. So basically the recommendation would be start with some more complex model so that they will have lower chance of lower chance of making a model misspecification. Right? So but in that case, if you use a complex model, you need to typically make sure that you have a relatively large sample size, right? Because you want to have a good classification accuracy, and also you want to consider the identifiability issue to make sure the model parameters can be uniquely estimated. Okay, that's something that we need to take into account. But you can always do model comparison when all the models can be estimated in from the our packages. You can always do model comparison and see which model will fit better. And I think if a simpler model can fit it up good, then we should always use simpler model, right? Because it's simpler. That's sort of the basic principle that we want to follow. But before you committed into a particular simpler model, you want to make sure that it does fit data well.
Yeah, thank you so much.
All right, thank you. So I know we're already a little bit past the time. So for the audience, if you want to leave, feel free to leave. But I still want maybe Dr. Ma address the one last question in the chat very quickly. I think the audience is asking about your recommendation for CDM handling like a hierarchical attribute, and also about like your opinion about like using some deep learning, machine learning methods.
Yeah, so let's start with the first one. The CDM model, which can consider the hierarchy of attributes. So I would put it this way. So the model that I have just presented are typical the measurement model component. The measurement model component build the connection between the success probability for each item and the required attributes. Okay, so we have many different models like DINA model, GISNA model, and just so many models. But in addition to that, so that's one thing we need to specify. But in addition to that, we can also specify the attribute hierarchical structure. So they are separate, there are two things. So you can specify a measurement model, and at the same time, you can specify how attributes relate with each other. Like attribute 1 is a prerequisite of attribute 2, attribute 2 is prerequisite of attribute 3, and so on. Okay, so you can build these two things separately, and in the JSON package, you can also specify them separately. Okay, which means if you have a attribute hierarchy, you can, in general, use any of those measurement models, but at the same time, you can specify the attribute hierarchical structure in the model. Okay. And the second question is about the application of CDMs with machine learning and deep learning. Well, this is a very broad question. I'm not quite sure about what you are referring to, but I think this is always an exciting direction. To the machine learning, deep learning, or AI stuff. I mean, they have a lot of potentials. And CDMs are tools for measuring students' attribute mastery status. So, I mean, if there's a way that we can combine those techniques to better serve students, I think that's always a wonderful thing that I think we should do.
Thanks so much for addressing the questions, and also thanks for our audience to ask a question. Yeah, I think we have a very insightful discussion and then today. Thanks everyone to attending our online workshop again. And I will make sure to post the recorded video through our DM SIGME, so you will be able to access the materials shared by Dr. Ma today as well.
Thank you, everyone. Thank you, Shi. Thank you, Yosu.
Thank you so much, and I hope you all have a great weekend.
Bye, everyone.
Bye.